Hello and welcome to Response I. Today we will be learning about Taylor series and how we can use them to expand transcendental functions into infinite polynomials. A Taylor series is writing a function, f of x, as an infinite polynomial in the form of a naught plus a1 x to the 1 plus a2 x to the 2 plus a3 x to the 3 all the way to infinity. Technically this is called the Maclaurin series, but I'm going to call it a Taylor series. Say you have a polynomial, let's say, I don't know, f of x is equal to 1 plus 2x plus 3x squared plus 4x cubed maybe, and we wanted to find each of these coefficients. Well, what we can do is use the derivative to cancel out terms on the left and plug in f of 0 to cancel out terms on the right. Let's try it for the first term. For the first term, a naught, that's just equal to f of 0 because that would isolate this 1 and get rid of everything else in the polynomial, and that's equal to 1. For the second term, a1, we can take the first derivative and we can find that f prime of x is going to be equal to 2 plus 6x plus 12x squared. So to find a1, we're going to plug in 0 again to get that 2. We get f prime of 0, and that is equal to 2. Now, something tricky happens when you try to find a2, and we need to fix this. We take the second derivative of that function, and we are getting 6 plus 24x. So a2 is not equal to simply f double prime of 0, but f double prime of 0 divided by 2, because the actual a2 is 3, and we're getting double prime of 0 is 6, so divided by 2. Apparently, this is a consequence of the power rule and multiplying by this exponent. So, it turns out for any n, a sub n is equal to the nth derivative of the function at x equals 0, all divided by n factorial. Because you have 4 times 3 times 2 times 1, and then you want to get that 4, so you just divide it by that 3 times 2 times 1, which is 3 factorial. I hope this makes sense. So, Maclaurin series say that f of x is equal to f of 0 plus f of 1 plus not f of 1, sorry, plus f prime of 0 plus f double prime of 0 all over 2 factorial plus f triple prime of 0, let's denote it like that, over 3 factorial all the way to infinity. And that is basically the Maclaurin series. So let's try it with a function, an actual transcendental function, not a polynomial. This function is f of x is equal to e to the x. So let's just plug it into this formula here. E to the x is apparently equal to f of 0 plus f prime of 0, all of that. So for e to the x, we have f of x is equal to e to the x. We have f prime of x is going to be equal to e to the x. We have f double prime is equal to e to the x, basic derivatives here. And it turns out that every single derivative is going to be e to the x. So every single derivative at x equals 0 is just going to be e to the 0, which is 1. So it'll be 1 plus 1x to the 1 plus 1 over 2 factorial plus 1 over 3 factorial. And we get that e to the x is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial. And then you could just follow this pattern. If if we wanted to write it for term by term, we would get that it's equal to x to the n over n factorial. So let's graph it, confirm our results. We have the function y equals e to the x right here. So let's just graph the first couple of terms, like 1 plus x. Y is equal to 1 plus x. It's a tangent line. What's that? That's not too helpful. Plus x squared over 2 factorial, which is x squared over 2. Ooh, look at that. The next term is plus x cubed over 3 factorial, which is x cubed over 6. And wow, that's really starting to snug up against this curve. If we do a couple more terms, the more and more terms, the closer it will end up getting to being, well, it'll just start looking closer. Like x to the 6 over 720. That is getting really close, snugging up against the curve. In fact, on the right, you can't even see the e to the x because it's so close. Maybe if we zoom in over here. Yeah, you can see that there's a very minimal difference. So, as the number of terms approaches infinity, clearly this function is going to approach that function. So, that's pretty nifty. Let's try with another function, like f of x is equal to sine of x. Well, f prime of x is going to equal the first derivative of sine of x, which is cosine of x. The second derivative is equal to negative sine of x. The third derivative is equal to negative cosine of x. And then the fourth derivative is going to be back at that sine of x. And then all of the derivatives repeat. So, if we plug it into this formula here, we have it looking like this. F of 0 for sine of x is 0. So it's going to be 0 plus f prime of 0. F prime of 0 is equal to cosine of 0, which is equal to 1. F double prime of 0 is going to be negative sine of 0, which is 0. And f triple prime is going to be negative cosine of 0, which is negative 1. And then it will repeat. So it'll just go in that 0, 1, 0, negative 1 pattern. So, ignoring all the terms with 0 as the coefficient, we get that sine of x is equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. And then we just use all of the odd terms because all of the even terms have 0 as a coefficient. So rather than graphing it, another way we can confirm that the Taylor series is correct is by using an approximation. If we wanted to approximate a number close to 0, sine of 0, we get sine of 0.5. Let's use the first couple of terms. In fact, let's just use 2 to approximate sine of 0.5. That's approximately equal to 0.5 minus 0.5 cubed over 3 factorial, which, after plugging it in on a calculator, you get 0.47917. Now, if you plug in actually sine of 0.5, you get 0.47943. So you can see that using just 2 terms, we have a very sufficient approximation. And using Taylor series, calculators actually use Taylor series to approximate terms of approximate transcendental functions. So yeah, and this function, I might as well go ahead and graph it because it does look pretty cool. We have sine of x here. We have the first term, that's x. We have the second term, minus x cubed over 3 factorial, which is 6. And look at that. It's really curving up. It's one of the beauties of mathematics. Yeah, so as you go to infinity and add more and more terms, it really starts snugging up against that curve. As you can see, if we were to approximate sine of 0.5, it gets closer and closer in the approximations. So, that's what Taylor series are, and in the next video we'll talk about other methods of power series expansions and manipulation.